Bill Farrell, who is going to give us our SSERVI highlight. This is a tradition we just started last year, I think, was our first one, maybe second. And so he's going to tell you a little bit about what the SSERVI teams have done this year. Thank you.
Right. Thanks, Yvonne. And I'm in the unenviable position of the last talk before you and your lunch. So. Oh, student. Oh, you're right. Okay, good. So I'm not. Okay. That's right. Okay. Well, as Yvonne said, what we want to do is go through some highlights that the SSERVI teams have been did over this last year or so. In particular, the highlights we want to focus on for this particular talk are exploration applications, not just all the highlights. Let's see, where's the clicker here? Oh, here we go. I will apologize to my fellow PIs before I talk. Some of this work is a little out of my wheelhouse, and I am sure I will mangle. Just recognize that I am not discriminatorily mangling. I'm indiscriminately mangling material, so that should help you feel better about the whole thing. Just talk a little bit about SSERVI itself. It's actually, there are 13 domestic teams with over 230 investigators. Funded investigators, and another 200 collaborators. It's actually a really big group, really kind of in the planetary community and actually beyond. 10 international partners. Now, at any given time, each team has many tens of activities going on, given that there's, 20 members on a team. A lot of parallel activity, and certainly in a talk like this, you can't go into depth. Even on one team, it would take an hour or more. But I would suggest that people grab some of those annual reports that were back of the room. You can actually download. I have the web page here. I mean, it's really spectacular. You can get into more detail. Actually, for the teams, they're really only 4-page reports, and you could actually, again, write a lot more about what the team's been doing. Now, in this talk, as I mentioned, rather than doing highlights across the whole spectra of our activity, we wanted to focus on highlights that sort of emphasize the boots on the ground, explore activity. That, how do we support AES and the things that Ben Bussey is doing on the human exploration side. And I'll say that each team provided a highlight. So there'll be 13 highlights. This is in no way comprehensive, but it's representative of the kind of work we're doing. And actually, it's actually pretty nice array. You'll get a flavor for what the teams are doing. It's pretty nice. So let's first meet the 13 domestic teams. Out of the University of Colorado, there's the Impact team with Mihai Harani as the PI, and they look at small-scale impacts, plasma charging, and they have that dust accelerator facility. There's the Center for Lunar Science and Exploration with the PI Dave Kring, who looks at impact history, geochemistry, and actually studies volatiles in the interior. There's Carly Peters' SEED team out of Brown University, who focuses on thermal and chemical evolution of planetary bodies, volatiles, and space weathering of Regulus, and other things as well, out of Brown. There's Bill Bakke out of Southwest Research Institute, looking at the formation of the terrestrial planets and asteroid belts, modeling the moon's origins and the origins of Phobos and Deimos. And actually, it works. Part of his team works on regolith properties as well. There's Dan Britt's team, class, out of the University of Central Florida, who studies the physical properties of regolith, hydration and weathering in NEAs, and dust charging and mobilization. The Vortices team, with the principal investigator Andy Rivkin out of Johns Hopkins, who focuses on volatiles, Regulus, and ISRU exploitation of resources. Of course, there's our team, DREAM 2, where we study the plasma interactions, exospheres, and radiation on airless bodies, exposed surfaces. Luckily, I'm not wearing the same shirt as I was wearing then. No, it's not good when you do that. There's Tim Glotch's team, RISE 4, who focuses on the remote sensing of airless bodies, analog field studies and operations, and actually looks at dust toxicity amongst other things. And of course, Jen Hellman has a great team, the Finesse team, right here out of NASA Ames, who looks at, does analog field studies, field operations, and actually sets up metrics for operation activities in support of human research, human exploration. And of course, there's the NEST team, Jack Burns out of the University of Colorado, who's looking at robotics, really astrophysics and the space environment, and in particular how the space environment might affect our radio telescopes on the moon. They're cleverly named the Expresso team with PI Alex Parker out of Southwest, looking at, whoops, I think I just hit the wrong button. Here we go. Looking at the characteristics of the surfaces and mitigating hazards, and also in robotic and human integration. There's the TREX team, Amanda Hendricks out of PSI, who looks at the spectral properties of the surfaces to derive surface properties, including ISRU, and hazard mitigation. And then, of course, there's the Reveals team with Tom Orlando, the principal investigator out of Georgia Tech, who looks at radiation chemistry, volatiles, and actually composite materials, amongst other things. And of course, there's SSERVI Central, who very gently shepherds us along with Yvonne, Greg, and Brad. Now, I always like this figure. This is this what I call SSERVI Science to Exploration Spectrum. Here on this side, you have sort of the more science-focused elements, while on this side, you have the more exploration-focused elements. Science elements include, for example, the origins of the universe, origin of the solar system, differentiation, and target body structure and composition. As you get more in the middle, you see things like geotechnical properties and volatiles and radiation that sort of have a kind of in the middle there between the two. And then on the far end, you have operations and human health and performance. What I want to focus here, though, is on this right side here, and the presentations, the highlights that the PIs gave me. Actually, they actually fall into addressing all of these subjects on this the right side of the spectrum here, including geotechnical properties, volatiles, human health. Now you can remap these into the strategic knowledge gaps. Now these are the knowledge gaps held by Ben Bussey at the Chief Scientist's Office, actually addressing the things we need to know in order to get boots on the ground. So they're really, for the moon, even though these are for the moon, they actually are applicable to really all the airless bodies in some sense. But one thing we want to know is, for the moon, is to understand the lunar resource potential. And here we're talking about resources in the regolith, for ISRU production, resources in the poles. Theme 2 is to understand the lunar environment and its effect on human life. Here in this case, we're talking about radiation and the biological impact of dust. And then a lot of the highlights actually focused under how to work and live in the lunar surface. Things like surface trafficability, dust, plasma environment, and habitat, life support, and mobility. So what I want to do is place our team's highlights in the context of these SKGs, sort of remap them back up through the SKGs. So let's first talk about understanding the resource potential. Regulus Resources, polar resources, and prospecting ISRU. And in fact, probably one of the big highlights we had in the last year, this last fall, was actually an updated new map of the OH surface abundance by SEED team members Ralph Milliken and Shuai Lee. This is Shuai Lee's thesis. Of course, SEED team is Carly Peters' team. And this new map is actually pretty spectacular. It's really showing that at mid-latitudes, you're starting to see a buildup of OH, of hydroxyl that goes all the way up to the poles. Of course, this is as measured by the band depth of the 2.8 micron IR absorption feature. SSERVI helped fund this, of course. There was always a lot of debate as to whether there was a diurnal effect, and Shuai showed for sure that you could see a diurnal effect in the data, kind of backing up some of the provocative work that Jessica Sunshine showed back in 2009. So this is really helping us actually get water from a rock if you held the rock up to the solar wind, and then in which case you could start making OH. And if you warmed it up, if you talk to Tom Orlando, you warm it up enough, you can actually start getting H2O, those OHs merging to make H2O. So really sort of this could even happen at an isolated silica grain moving in the inner heliosphere. It really makes the potential to make water sort of universal. Of course, moving on to the poles, Dave Kern an example study of how to use it times when humans aren't there. In particular, what they did is they looked at one of these ISAC design reference missions where we would have 5 landing sites, human landing sites, in and around the South Pole region. And then what they found is that you're going to if you put one of these lunar electric rovers around on one of the flights, there'll be a whole year where there's nothing going on. Well, you could actually start using these rovers to start prospecting for water resources during the downtime between landings. And so they showed, like, for 12 months between human landings, you could start having these rovers drive along and on their own, going, and in this case, they were looking at going in and out of Edmondson Crater, and you can see they were going into regions where there's permanently shadowed and into really cold regions. And actually, in this case, they actually considered putting on a ground-penetrating radar to look for the base of any ice layer. So it's this cool study kind of talking about what could happen up at the poles in terms of prospecting and ISRU. Now let's talk about understanding the environment and its effect on human life. And there are a couple really nice highlights here, particularly on the biological impact of dust and on radiation. First, the Trex team, Amanda Hendricks' Trex team, has one of the things that they're doing in the lab is they're trying to get spectra from the UV all the way to the IR on the fine grains. And what they want to do is, based on those spectra, they want to go back and look at the spectral maps of the moon and actually produce a grain-size map of the moon, not only for resource potential, but to understand the dangers and hazards of fine dust, pointing out places where you might want to go. And of course, what Amanda pointed out in her slide is, that this fine dust could be a problem. She quotes this Gene Cernan quote: "Dust is probably our greatest inhibitors to nominal operations on the moon." So this would be a way to mitigate the danger by simply saying, don't go to these regions where you might have a lot of fine grains. Of course, one of the reasons why you worry about this was studied by the RISE 4 team. They actually have a group of a pharmaceutical group at Stony Brook, who actually has been, I think it's a Rachel Caston, this was her PhD thesis, where they actually incubate cells in lunar regolith. And in particular, they had neuron cells, and A549 is actually lung tissue. And you can see that the cell survivability, particularly in this glutenate material for lungs, was actually pretty low, cell viability, when you start mixing with these simulants. They also did DNA testing, and as it turns out, again, this is a little out of my wheelhouse here, but in essence, you can see the DNA effects were somewhat not quite related to the viability. And what they suggested is that maybe the cell's viability wasn't necessarily connected to DNA damage, but maybe some other process was killing off cells. For example, in this lung tissue here with this agglutinate simulant. Of course, the reason why we worry about this is sort of the specter of what happened in the 1930s with the Hawk Nest Tunnel in West Virginia when workers were exposed to newly milled silica. And there were hundreds of deaths from acute silicosis. So if you leave explorers out there exposed, they bring the dust in their suits, and they take their suits off, and this goes on. And there's long exposures to this dust. Could be a problem. So you want to avoid these kinds of things. This is not good. Also, with regards to radiation, one of the what we've been doing on the Dream 2 team, Nathan Schwadron in particular, he noted that he and his team radiation noted that over the last 3 or 4 solar cycles, the solar max and min, the solar cycles have been getting progressively weaker over the last 3 solar cycles. And as a consequence, the galactic cosmic ray flux has been increasing on a cycle basis. The maximums have been getting higher, and the minimums also have been getting higher in association with the reduced interheliospheric magnetic shielding. They then can model this, and actually they calculated the allowable astronaut days, and they're decreasing, generally decreasing over the last 3 solar cycles. And he has a new paper out talking about how the GCR flux, galactic cosmic ray flux, is even higher now than it was back in 2014 when he did this original study. And of course, these are things you have to worry about. Whoops. These are things you have to worry about. For example, the deep space gateway, and if you have boots on the ground back on the moon, these effects of these GCRs. 2 minutes, okay. So the third SKG topic is how to work and live on the surface, and there are a large number of highlights under this group. In particular, Dan Britt is doing simulant studies of a whole series from a whole series of bodies with applications for human health and radiation shielding and ISRU. What he said yesterday is that simulants are currently available in small amounts, and I heard him say for free, so if you want some, give him a call. Bill Bakke actually did a fundamental, and his team, Sanchez and Shears, actually did a fundamental science study on Regulus Cohesion, where they found that if you had Regulus on a fast move rotating asteroid, that if you didn't include cohesion, the Regulus would, let's see if I can do this here. The Regulus comes off as let me see, I think comes off as pieces. Now here we go, we'll just do, comes off as individual pieces, whereas if you include cohesion, the Regulus comes off as aggregates, as chunks up off the surface. So this, of course, is important because Regulus was sticking in the Apollo spacesuits here. You know, the fibers themselves were about 20 microns in width, and the Regulus stuck to it. And actually, and the grains get stuck to the suit for about 3 decades. You know, still stuck there, in fact. And the grains stick to each other as well. The Vortices team also studied Regulus geotechnical properties, including thermal conductivity and thermal fatigue, suggesting that thermal fatigue can more rapidly degrade surfaces, rocks, than micrometeorite abrasion. Now, if you have Regulus and you add dust to it, or if you have a Regulus and you add a plasma to it, you can actually get the plasma to move and become dynamic. In particular, photo electrons or UV emission can shine on these surfaces. And you can actually get charging, differential charging, which then makes the Regulus pop. And let me see if I can get this movie to work. Let me go.
Hey, Bill,
yeah.
I was wrong. You have more time. Greg's taking over. I've got to run.
Okay.
Great talk.
Okay, so I have more time.
Yeah, you do.
You have a total of half an hour, not 15 minutes.
So okay, so, wow, okay, good, thank you. Jeez, I was like, I'm not sure I could go into overdrive, but, you know. So, okay, good. So let's see if we can try this movie then. Yep, there we go, right here. So good, let me explain this then more coherently. It looks like right here, you have these subsurface cavities, and UV photons will shine on part of this cavity, and you'll get secondary electrons emitted, and the electrons will actually coat the grains, part of the grains, while the other part of the grain where the UV is shining charge is positive, the other parts collect the electrons and charge negative, and that strong differential charging creates supercharging, which allows the grains to pop. So let's just see, let's see if I can get this to go. Can you get that top movie to run there? Let me see, let's try this. Ricky, let's see if I can, there you go, that top movie, right? Let's see, the top one. There you go. There you go. Okay, good. So you see how the grains are popping out there? And again, these are insulating grains. And that's why this works. If they were conducting, you wouldn't have this differential charging. But the grains are hopping all over. What's more is the grains are not, when they get onto a flat surface, you notice they're not hopping. That's because you don't get the cavities. And that may explain part of the, Jack, part of the things that you were talking about where you don't see grains hopping on rocks. But on the Regulus, but in the Regulus, we can get these cavities, you can get them going. How about getting the movie down below going as well? Okay, so now if you added a magnetic field to this, and they just put magnets, you can see that where you're blocking the solar, the incoming plasma, you're not getting the grains to move, but in regions around that, you're getting, strange-looking dune-like features. So it's all very interesting, what's going on. This is, you add plasma to the regolith, and you get some dynamics going here. Now, of course, the reason why you have this is because these are insulating grains, and this is a backup slide in case the movies didn't work. You could actually have human systems start undergoing differential charging too for basically the same reasons, which is one of the reasons but the Reveals team is looking at graphene nanocomposites to actually make a more conductive types of surfaces. And what they're doing is they're making these, they're developing these composites and actually doing a whole array of tests on these, including strength tests, flexibility. Like here's this is their UC Davis part of the Reveals team, Tom Orlando's Reveals team, doing stress strain analysis, thermoelectrical conductivity, and repairability and dust adhesion. Of course, where you would apply these is where you'd use these is on EVAs. When you're walking around, you'd like a suit like that, and that's exactly what the Finesse team, Jen Heldman's team, is doing. They're doing analog field deployments where they're doing EVAs and doing ops support here, testing out portable instruments, doing science, and they're actually doing robotic human integration with these UAV flights. Of course, one of the things you worry about when you have this telerobotic operations is latency and lag. And this is where Alex Parker's Expresso team has been working. They've been looking at latency compensation and actually using gaming technology to look at this. They call it an antagonistic neural network, but actually if it's getting rid of the latency, I think of it more as a friendly network, but why they call it antagonistic, I'm not sure. But basically what they do is they take images, frames, and they actually identify static elements relative to dynamic elements. And then with the dynamic elements, they move ahead, they extrapolate probabilistically so that if you're delayed, you actually can you use the extrapolated image until the real image shows up. So this is the way they're battling some of these real life ops issues using gaming technology. And of course, where you would apply all this is for telerobotic operations of a sophisticated system like radio astronomy arrays on the lunar night side. And actually, and this is part of the Nest team, Jack Burns' Nest team. In fact, they had a really big find this year where Judd Bowman, one of Jack's co-Is, looking at 80 megahertz, detected what is called cosmic dawn. It's actually what they're looking at here is the 21 centimeter line of hydrogen Doppler shifted, going back in time so far that that 21 centimeter line is now in the low frequency of the radio. And what they're seeing is when the stars first turn on, the emissions affect the hydrogen cloud, and you get an absorption feature. And this was just discovered. They just detected this, came out as a big study, great find. But there's also another absorption feature called the dark ages, and this is when the cosmic microwave background gets absorbed by the cold hydrogen cloud. That's down at 10 megahertz. You can't study that from Earth. This was done at Earth. You need to get away. You need to get away from the Earth, and actually the Moon is the best place since it's radio quiet there. And I know he's looking at small sat studies being deployed, small sats being deployed at the Moon to examine this. So let's see. But to build one of these networks on the lunar far side or on the near side, through teleoperations, you'd have to really complete all the knowledge gaps that we were talking about before. And of course, it requires some planning, and that's exactly what Carly Peters' SEED's team is doing. They're actually training the next generation of scientists and engineers. In this case, they have Brown and MIT scientists and engineers coming together, working together to to understand how you would implement these processes in order to work and live on the Moon. And in particular, they've been with astronaut David Scott. They've been doing design reference missions for, that include enhanced human-robotic interactions for long-duration missions, 500 days or so, for 500-day missions on the moon. So doing these kinds of things, you're planning ahead, incorporating all of the knowledge that you've learned by satisfying these knowledge gaps. So finally, this brings us to the transformative lunar science. And even though that's more on the science to exploration spectrum, more on the sciencey side, there were some exploration SKGs reflected in understanding the water and OH cycle at the moon, and in looking at the space weather and plasma surface processes. There's also a whole section on this report on exploration leadership, the need for infrastructure, again, to make the far side accessible, human-robotic partnerships, and commercial involvement. And so with that, I think I'll stop. Hopefully I'm in time. Okay, all right, good.
Thanks, Bill. Great. Thanks for such an excellent job representing the great work that all of you guys do.
Yeah, they did good. I mean, the PIs did a great job handing in some terrific work.
Absolutely. Yeah. Thank you. So let's take time for maybe just a question or two before we go to the student lightning round talks. Any questions? Jack.
I think we can all agree that you don't want to breathe and inhale or get seriously exposed to lunar dust physiologically, but let's don't get carried away. There are engineering solutions, and you can scare yourself to death here and scare other people who might have other reasons not to want to do what we want to do. There are clear-cut, layered solutions, engineering solutions to preventing the inhalation or exposure to lunar dust. And it's there, we know it's there, so let's be careful.
Right. No, I agree. I mean, one of the things I talk about is, having the suits remain on the outside and you enter them through a suit lock sort of thing.
Yeah, that was proposed out here at Ames decades ago and was implemented in the Lunar Electric Rover or whatever, Exploration Rover, whatever it's called now.
Right.
And yeah, that's an obvious vector, or dust vector that you can get rid of. The lunar dust, at least, is magnetic for the most part, so you can use electromagnetic filters for any dust that happens to creep into your habitat. It's just, and they're fairly simple, straightforward solutions. You need to do anyway. You need to keep dust. As I'll talk later this afternoon. Now I understand. You need to keep dust off the suit. You might as well plan to do that for other reasons. It just bothers me a little bit. It has for decades that we tend to try to scare ourselves a little bit about dust. I breathe it 4 times, and except for my intellect, which is probably deteriorating for other reasons, I don't know of any adverse effect. But you still don't want to do it. It's ridiculous to expose yourself to that based on our terrestrial experience and just good common sense.
All right.
Thanks. Tim.
Yeah, just in response to what Jack mentioned, I'll just point out that there's a peer-reviewed open access paper describing that study in the journal GeoHealth as part of the SSERVI special issue by Rachel Caston, who Bill mentioned. One of the takeaways from that paper, I think, and just like Bill, I'm not an expert on this stuff. I'm a geologist, not in the medical school. But from the acute exposure standpoint, at least with the simulants that we used, and we recognize that we need to go to the next step and use actual lunar material, a lot of the effects are not necessarily as bad, worst case scenario, as bad as you would think. But I think there still is a very open question as to the long-term consequences, and that's where this kind of the mitochondrial nuclear DNA study came in, and that's just a unknown, and I think it's worth pursuing.
I'm just saying, take the engineering steps so that you don't have to worry about it, and let's worry about some important things. And,
fair enough. Yeah. If you can
if you had long-term exposure to dust, you probably will have some effects. But let's don't have it. Martian dust is going to be a little bit more of a challenge because it's not magnetic. But still, I think there are a variety of filter systems that one can develop in order to take care of that with the The ultimate thing is don't bring it into your habitat.
I agree with that.
All right, well, let's thank
Okay.
Bill again.